Hello and welcome to Ask Echometer. Today's session is titled Shut-in Fluid Levels in Today's Environment, Part 1. And we'll be hearing from Dieter Becker, Gustavo Fernandez, and Dr. Tony Podio. So gentlemen, I'll turn it over to you now.
Thanks, Carrie Ann. And I'm Dieter. I'll be going through the slides on the first part, but we're doing a little different format on this, and we're kind of showing you more of the Echometer team. So this is going to be more of a panelist discussion, and Tony, Gustavo, and myself will be involved in this, but we have other people at Echometer here too. You saw Carrie Ann, Ken's in the chat. I see Lynn's with us, so any one of us might come in and just comment on slides. So this can be a little more casual, more of a panelist discussion. Now you're welcome to make comments via the chat, post questions to the chat as Carrie Ann suggested. But we're gonna look at an outline of today's discussion. We'll start out by saying this is part 1 of a series. And we're gonna have some upcoming sessions on this. But in today's session, we're gonna focus more on pumped wells and just look at the big picture. Upcoming sessions might be go into more detail of calculations such as gradient calculations. We will look at gas wells and gas lift wells, see how the calculations apply to them, a little different than pumping wells. We'll may look at unattended or remote operations for collecting the data. We have a device called a RAM. And then if we get this data automatically, that's pressure transient testing. And we may look at what we can do when we return wells to production. A drawdown test, perhaps using the RAM, watching a gas lift well unload, things like that. But that'll all be in the future. Today's kind of a part 1 of a series where we're looking at the big picture on pumping wells. We're going to discuss the benefits of shutting in a well today. And why do we even want these static bottom hole pressures? Look at some practical considerations for doing this, and then talk about how a static bottom hole pressure fluid level is different from a producing bottom hole pressure. We're going to look at the big picture of the calculations about the fluid distribution in the well bore and so on, and then we'll take a break for some questions and answers at that point. And after the break, Gustavo will drive the presentation looking at some example data in the TAM software and how it calculates the static bottom hole pressure. And once that's complete, we'll stop for another question and answer period. And Tony will jump in with discussions on inflow performance relationships and determining the maximum producing rate out of the well, the Qmax or the pump off rate. And then a little summary and another question and answer period at the end. So we're glad y'all are here. And but today's environment gives us a unique situation in terms of getting static bottom hole pressure. It's an important number, but often it's a difficult number to obtain. And usually during normal times, we're trying to maximize our production. We have to shut wells in to get the static bottom hole pressure, and we don't want to shut them in because we don't want to lose that production. We don't want to lose the revenue stream. So in today's environment, we have many wells shut in, and we'd really like to emphasize that this is an opportunity that we don't want to miss when we go out there and get these static liquid levels. We have a unique situation now that makes it a lot easier to get the data. So in doing this, we're going to talk about planning the static bottom hole pressure test, perhaps inspections we want to do on the wells, instrument selections, about how we're going to acquire a producing liquid level before we shut in a well. We're going to talk a little bit about the wellbore itself and the wellbore integrity. And maybe you have an older wellbore where the integrity is not that good, where you don't want to close the valves, and what we can do in a case like that. we're going to talk about just other considerations, like do we stop the pumping unit with the horse's head up or down. But why do we need the static bottom hole pressure? Why do we want to take advantage of today's environment? Well, one of the things we're going to emphasize today is that we need the static bottom hole pressure information to determine the well's potential. If we really want to see how much production we can get out of this well, we need to do our inflow performance calculations, and the static bottom hole pressure is a key piece of information that goes into that. We need that to properly size our production equipment, whether it's the artificial lift equipment at the well or the equipment at the tank battery, and to look at our production efficiency. Again, this will give us a maximum production that's available out of the well, and plan on sizing the equipment for the maximum pump off. We'll also get the depletion off of this. We'll see how much the reservoir pressure or the static bottom hole pressure is changing with time. And I use the word static bottom hole pressure and reservoir pressure interchangeably. And even if we acquire static bottom hole pressure on several wells throughout a field or a lease, we can compare that to see how the depletion is changing throughout the lease. This also provides data that we might use to calculate the reserves remaining in the field. So what do we need to do to get a static bottom hole pressure test? Well, typically we would need management approval in the normal producing time. But most of the managers would rather have the production and the money in the bank instead of the number for the static bottom hole pressure. So we should really take advantage of times when there's a planned shut-in, and we shouldn't miss this opportunity. I've worked in the field at times where there was a turnaround at the gas plant, and there was no place to go with the gas, so the entire field was shut in. That is an ideal case to get static bottom hole pressure. Today, we might see a lot of storage facilities at capacity, and we're having to shut in wells because storage is at capacity. Again, that's an opportunity that we shouldn't miss. Perhaps if you're working offshore, there might be some maintenance or other considerations going on the platform that shut that well in. In the normal, so we want to take advantage of today's environment where we have shut-in wells to get this information. In the normal times where we're trying to get all the production that we can, I try and take advantage of when the well's down for mechanical problems. Perhaps there's a rod part, and it might take several days to get a pulling unit or a rig out there before you can fish the rods and get the well back on production. Again, the well's down for a mechanical problem. Take advantage of it and get the data. Perhaps there's a motor failure, or the belts are down, or there's a flow line leak, or any other number of situations that cause the well to be shut in. Let's take advantage of these and get the static bottom hole pressure. Now, there's differences in obtaining static bottom hole pressures and producing bottom hole pressure, between producing liquid levels and static liquid levels. So we're all used to acquiring producing liquid levels. This is something we do routinely on a day-to-day basis. We go out there and we shoot liquid levels on producing wells. Now, these tend to be noisier, especially if there's gas production in the well. We tend to have more background noise. We have a gaseous liquid column, so we have to correct for the amount of gas in the liquid column. And generally, on a pumping well that's in a steady state or a stabilized condition, all the fluid in the annulus, the liquid in the annulus above the pump, is oil. Now, a static bottom hole pressure, we do that on a well that's been shut in long enough for the pressure in the wellbore to equalize the reservoir pressure. So that means there's no more fluid flowing in or out of the wellbore. The well's shut in, it's equalized to the reservoir pressure, it's static. So this also means that the well's quiet. It's easier to obtain a liquid level. You might not need as big of a shot, a fairly small shot, to obtain a liquid level. The liquid columns are solid liquid. There's no gas percolating through that liquid column. There's no gaseous liquid column. And now the fluid in the annulus, when it's staticked out, we can have both oil and water in the annulus, dependent on the production rates. And we're going to talk about that in our calculations. But one thing we want to make you aware of is that a producing fluid level cannot be used to calculate static bottom hole pressure. A number of us have worked with customers on producing shots where they obtain a producing bottom hole pressure, and then they turn around and say, well, the program can calculate a static bottom hole pressure. Let's calculate a static from the same shot. That's not true. We have to shut the well in long enough to static that out. And that depends on the area that you're working in, how permeable the reservoirs are. That depends how long that's going to take. And we're going to get into that in a few slides. So as we prepare the shut-in, we want to make sure that our team's aware that the well is shut in. You know, today you might have a field that's shut in because you can't sell the oil, your storage is full, but you ought to practice a lockout, tag out practice, just so nobody comes behind you and turns this well back on while you're having it build up to the reservoir pressure. You also want to verify the condition of the well and make sure that you have that your pressures won't exceed the safe working pressure of the well. You'd like to make sure there's no leaks, and that your stuffing box on a rod pump well, that the stuffing box is in a good enough condition that it won't leak as the pressure on the well increases. Now we need to be especially vigilant on our older wells. And our older wells, where the wellbore integrity might not be very good, we might want to consider something else. If we don't think we can close in the valves and they won't, the wellbore won't withstand that pressure, perhaps we can try leaving the valves open, and hopefully the liquid production in the well will kill the well, and we'll still be able to obtain a static. But in general, we prefer to have the well shut in to obtain our static bottom hole pressure. Also, before we shut the well in, we'd like to get a good well test. We'd like to get a good baseline production rate. And this is a good information to have. We like to get as much information to solve the questions on the well as we can. And one of those is the production rate. We're going to see in the calculations that we're going to calculate the fluid distribution in the annulus of a pumped well, how much oil and how much water we have. And that baseline production rate is key to that. So preferably, we would have a well test, a production rate test, performed very close to the time that we're going to shut the well in. We'd also like to have a producing fluid level on the well prior to the shut-in. And Gustavo will work through an example. He'll show you how this is used. But again, that producing fluid level is used to determine the fluid distribution in the well bore after the shut-in. We assume that all the liquid above the pump in the producing state is oil. And then that's the starting point for the afterflow that gives us the fluid distribution after the well is shut in. So today, our wells have been, we have a unique environment here where our wells are actually getting shut in because there's a lack of storage. And in this pricing environment in the oil field, this is the first time I've seen a widespread shut-in due to a lack of storage. In the early 80s, I've seen this on gas wells, where gas wells was shut in because there was no market for the gas. But that had different problems related to that. That had leasehold issues with it. Because once a lease is past its primary term, it's held by production. And most of the leases require that you produce that lease 1 day a month to hold the lease. So in the gas wells that we had shut in the 80s, because there wasn't any place to go with the gas, the pipeline would allow us to open them up 1 day a month to hold the lease. Now, Your land department's probably looking over all of this, but you want to make sure that's not being ignored. In today's environment, we may have long-term shut-ins, a lot longer than we'd normally shut in a well. And hopefully things will turn around. I understand some wells are already being returned to production, but we might see some things due to this long-term shut-in that we normally wouldn't see. We might see some wellbore damage come about. We might want to think if we need to use some corrosion inhibitor or do something to pickle the well to prevent corrosion. We may have fill come in the well as it's been shut in for a long period of time. In the formation, we may have cross flow. We may have mingling of incompatible fluids, and all this might lead to some reservoir damage. So, we have to wonder, will this well come back after an extended period of shut in to the same level of production that it was before it was shut in the first place? And I'm more concerned about the marginal wells. The good wells will probably come back better than some of the marginal wells might. But again, in a case like this, if they're going to be shut down for a long period of time, I think it's a good practice to get an additional baseline information before we shut the well in. We may want to run a dynamometer test if we know we're going to shut this well back in, just to see what a normal dynamometer looks like. And that way, if it comes back on and the well's not making the same production, is it a reservoir issue or is it a mechanical issue? And we could run a dynamometer and compare it to the baseline dynamometer we had before we shut it in. If it's a plunger lift well, we may want to track the plungers before we shut the well in. Because if we have problems afterwards, again, is it a mechanical problem? Did we have some corrosion come in, holes in tubing, scale formation, things that might be affecting the plunger travel, or was it a reservoir issue? So again, it's nice having a baseline information, so if we do have problems later on, that we can help troubleshoot and determine the cause of the problem. Now, the bulk of this test, this session here, is really talking about just getting a single static bottom hole pressure after the well's stabilized at the reservoir pressure, the static bottom hole pressure. But another approach is to do pressure transient testing, and we'll talk about that in future sessions, where we collect data during the time that the well is shut in. And instead of just having one point at the end, we collect multiple points along the way. And this allows us to calculate more information about the reservoir. It allows us to calculate permeability. A big number we get out of that is the skin factor. That's a number that tells us how bad the damage on the well is. So if, again, we anticipate having some reservoir damage during an extended shut-in period, it would be nice to have the pressure transient test as an early part of the shut-in so we can see what our baseline reservoir properties are before we shut it in. Tony, Gustavo, anybody have any comments before we proceed?
No, not at this time. I think you're doing a real good job.
When a well is shut in for an extended period of time, the pressure at the bottom of the well bore equals the reservoir pressure. But that pressure in the well bore lowers depending on the production rate. And the higher the production rate, the lower the pressure we get at the bottom of the well. And later on in this session, Tony's going to talk about inflow performance relationships, where we're comparing this producing bottom hole pressure in the well to the reservoir pressure, the static bottom hole pressure, to determine the potential of the well. And this pressure here in the bottom of the well bore is dependent on the rate. So if the rate's 0, it should build up and equal to the reservoir pressure. One of our calculations that we're trying to do is figure out how much production we can get out of the well, which will bring this to a minimum pressure for a producing bottom hole pressure. So the static bottom hole pressure is also known as the reservoir pressure. pressure. And I use those terms interchangeably. But it's the reservoir pressure at the edge of the drainage radius. So it represents the pressure that's available to push the fluids to the wellbore. So if a well is depleted and that pressure is low, we don't have a lot of energy in the reservoir to push the fluids to the wellbore. If we have a strong reservoir, we have a lot of energy available to push that fluid to the wellbore. So as the pumping rate increases, we have additional drawdown, and that's going to lower this pressure in the wellbore. At the drainage radius out here, at the pressure out there, we're going to have the reservoir pressure. And we're going to see, depending on our reservoir properties, a profile of this fluid flow into the reservoir. So the static bottom hole pressures are driving pressure, pushing our fluid into the wellbore, and then depending on the rate, we stabilize at a certain producing bottom hole pressure. So generally, during normal times, we don't have a good way to come up with this number, the static bottom hole pressure. So we're having to guess at this number, and we're guessing at a number to put in either the TAM software, the TWM software, or anything else we use to try and calculate the potential of the well. So really, to calculate the well's potential, we would like to have the static bottom hole pressure within about 15%. For other things, that's in terms of reserves and depletion, we'd like to be much more accurate than that. But if we're trying to size our pumps and so on, 15% would probably be good enough to get us in the ballpark on sizing our artificial lift equipment. So we'd like to get the static fluid level, the static surface pressure on the well when the well's down for any reason, whether it's a mechanical problem or today's environment. Today we have different software packages that can calculate the static bottom hole pressure. And I would say TAM, the Total Asset Monitor software, is our flagship software. That's used in conjunction with our fluid level shots and our equipment to calculate the pressure for you. TWM has been around a long time. It's a mature software package used with our wire well analyzer. And the AWP software is a software package that's available where you can, it doesn't have to be tied into any particular set of equipment. You can just type in the numbers from fluid level measurements and surface pressure measurements to compute the static bottom hole pressure. So to calculate the static bottom hole pressure, we're going to add up different parts of that. And this slide shows where we take the casing pressure or the surface pressure on the well. To that, we add the gas column pressure, the pressure due to the weight of the gas column, the pressure due to the weight of the oil column, and the pressure due to the weight of the water column. So each of these columns will have a gradient, and we calculate the gradient of these columns in our software. Today's session, we won't go into those gradient calculations, but in future sessions of this series, we'll touch on those gradient calculations. Now, there is one part that's not on this slide, and it's really insignificant in most static bottom hole pressure calculations, which is why it's not here. And that's the atmospheric pressure. The atmosphere also applies a part to that. And that becomes more critical when pressures are low. But if you have a higher static bottom hole pressure, that number becomes insignificant. So again, this has to be when all flow has stopped from the reservoir, the well's shut in, and it should be a quiet, stable environment. So in this case, we probably will have a lot easier time obtaining a fluid level measurement. We probably don't have to put as much gas on our gun to shoot the fluid level because it won't have the noise from the gas production coming up the well. Some people will say, I don't know how long this well has to be shut in to obtain the static bottom hole pressure. How long does it take to static out? Well, in that case, just come out there and shoot that fluid level every few days. And when you see that it's changing, then you know you're see that it stops changing, then you know you're staticed out. Perhaps you have a SCADA system out there and you're measuring the surface pressure on the well, the casing pressure. And even with that, you could just monitor the surface pressure. And when it quits changing, you have an idea that the well's staticed out. So if you've gone out there and you've shot a few liquid levels over a period of days, see when it's changing, only that very last one should be used as the static shot in your calculation. So on these calculations, we're having oil and water in the wellbore. And it's a little bit difficult to predict how much oil and water we have in the wellbore. It's because we don't know the production rates from our different zones. All we can assume is that the water-oil ratio will remain constant from what it was from the well test that we had before we shut the well in. You know, in reality, it's going to change a little bit because perhaps a zone with higher pressure might make more water. So we don't know exactly what it'll do. So we can only assume that it's going to be at the well test we have before we shut the well in. Now, if you really want to get an idea of what your range of accuracy might be, you could do these calculations two different ways. You could do it one, assuming the well produces 100% water, and see what you can come up with a static bottom hole pressure, and do another set of calculations where the well produces 100% oil. And those would give you the extreme ranges of possible static bottom hole pressure. But hopefully we will get you closer by assuming the water-oil ratio in the last producing liquid level before the well was shut in.
Dieter, one comment. Today, it seems to me that a lot of people do not do a very good job of measuring the water. And so the water-oil ratio is an assumption. But on the other hand, this is not very important as long as the difference in density between the oil and the water is not significant. So if you have, say, producing 20 API oil, it's not as critical as when you're producing 40 API oil.
Thanks, Tony. So let's look at how we calculate the amount of oil and water in the annulus during the shut-in period. We mentioned we want a producing liquid level before we shut this well in, and this gives us a baseline. This gives us the amount of oil in the wellbore we have while we're producing. And we use the gas-free equivalent of the liquid column in the well. That's our baseline. And then if we shut this well in to get a static liquid level, and we see that the liquid comes up 1,000 feet in this well, this well might be making 40% oil, 60% water. We know that 40% of the 1,000 feet of fill-up is oil, or 400 feet of oil. And 60% of that fill-up, or 600 feet, is water. So altogether, after it's shut in, we have 900 feet of oil. The 500 feet that we started with, and the 400 feet from fill-up, and then we have the 600 feet of water from the fill-up. So this is how we compute the percent oil and water in there, assuming that the water-oil ratio in the well remains constant. So when we shoot a producing bottom hole pressure, we only need one fluid level measurement. We need a surface pressure measurement, and then we get a buildup on the surface pressure, and that helps us determine how gassy that fluid column is. The static bottom hole pressure ideally requires two fluid levels on that well. One for that producing shot, as you saw on the previous slide, to give us the baseline information, and then the static bottom hole pressure shot after the well's static out. A lot of times, if you had mechanical issues and so on, you didn't have a chance to get that producing bottom hole pressure shot ahead of time. But you have an idea where it was. You know, if you don't have any information, our software assumes the well was pumped off and all the fluid in the annulus is in the producing rate. So here's an example of the producing bottom hole pressure in the report in the TAM software. And then in a little bit, Gustavo will walk you through the TAM software and show you how these calculations are done in the software. But we start out with a producing shot. It needs the baseline case, and we either have to pick a producing shot or manually type in the producing liquid level, the percent gas in the liquid level, and it then uses that as the baseline to calculate with the static shot to calculate how much oil and water you have in the annulus afterward. So again, this is the scenario on a pumped well. In future parts of the series, we'll talk about flowing wells, gas lift wells, where this scenario might be a little bit different. But once we calculate the amount of oil and water in the annulus, we give you a pressure profile. So we see the gradient through the gas column in the well, then the gradient corresponding to the water column in the well, and then the gradient in the oil column, and then that gives us the static bottom hole pressure. And again, on a static shot, there should be no casing pressure buildup here. There should be no more gas coming into the wellbore. So I often use this casing pressure buildup on a static shot as a quality control tool. I use it as a method to see if I still have gas flowing in the well. Ideally, it doesn't go into the calculations. It's just an image there to show you how much gas is coming in. And you might notice we calculate the annular gas flow from that buildup, and in this case, there's zero gas coming into the well. So as I mentioned, in a few minutes, Gustavo is going to go through this in TAM, but we see we have the production case in the worksheet and then the static case. And what you can do is you can select the producing shot you had right before you shut the well in, as was used in the report that we looked at here a minute ago. If you don't have that producing shot, you can manually enter the liquid level, the percent liquid in the column, so it knows what percent of the column's liquid and gas, and you can manually input the well test prior to that. And that will help it calculate the amount of oil and water in the gas. If you have the producing shot, it's a lot easier because it pulls all that information out of the producing shot. So let's talk about what do we need to come up with an accurate static bottom hole pressure. We need that well to be shut in for a period of time sufficient to stabilize the casing pressure in the liquid level. So we don't know how long that is if we're not familiar with the field. If you're familiar with the area, you might say a 72-hour test is sufficient. It might take 5 days. It might take a week. If you don't know, just shoot fluid levels and measure the casing pressure along the way. And when the numbers quit changing, you know you're static out. We need a accurate determination of the fluid level. We need to measure the surface pressure and the pressure buildup rate at both the producing and the static conditions. And we'd like to know our oil, water, and our annular gas density. So knowing the good fluid properties is good. We also need a good wellbore description. And this is an area I sometimes see lacking on fluid level shots. You know, we need to know if there's any changes in cross-sectional area. We need to know, for example, a liner. We need to know where the pump is sitting relative to the producing interval. You know, historically, the pump has been on our vertical wells, especially in hard rock country like the Permian Basin. Our pump's been below the producing interval. These days, we see different scenarios. With horizontals, we often see the pump above the producing interval. So we need a good wellbore description. In that fluid level analysis, we're going to pick static as opposed to producing, and then either enter the last fluid level shot or the production in the static bottom hole pressure. I mentioned a few times, how are we going to know if this well's static out? And let's just cover that one more time. We can do that with periodic fluid levels, see if they're changing. Periodic casing pressure measurements. So even if you have some telemetry or SCADA systems on the well and you don't go out shooting the fluid level, just measuring the surface pressure on the well is going to give you an idea that the well's static out. If your casing pressure buildup's flat and you're not building up casing pressure, that's a good indication that the well has static out and you're in a good spot to measure your static bottom hole pressure. And that brings us to a good point, and see if there's any questions on the first part of the seminar. And
yes, we actually have a few questions, and let me start. I'll have some questions for you. So someone's asking, I think Dan from Capstone is asking, it's a quick and easy question. Just he doesn't remember. On the mechanical wellbore setup for tubing and casing, for the top, do we enter 0 or the Kelly bushing distance?
I prefer to enter the Kelly bushing, because when the wells are drilled, everything historically has been measured from the Kelly bushing on the drill floor. It's still measured from the drill floor. So especially in today's rigs that are big drilling rigs used to drill perhaps these shale wells, that KB correction is perhaps 25 feet. So ground level is already 25 feet into the well, because you're measuring from the rig floor and the ground's 25 feet lower. So putting the KB in for the top of the casing or tubing is an acceptable practice. I might even go a little bit farther. Let's say the KB correction's 25 feet and the casing is a foot above the ground level. Then I might take 25 minus that 1 foot and put 24 feet for the top of the casing. Let's say the tubing is 3 feet above the ground level and the KB is 25 feet. I might say that the top of the tubing is then 22 feet, because that would be the 25 feet minus the 3 feet that was above the ground level. So thanks for asking that question.
We have a question. We have a few questions from Ken too. And the question is, how does this work in a water flood where you're injecting water in a nearby well?
Well, as you're injecting water, that's going to provide reservoir support. So we don't do the test any different on our static bottom hole pressure test. We're still going to do our test of what's same, wait for it to stabilize. But as we talk about pressure transient testing, we're really kind of mentioned it here in terms of getting reservoir pressure. But there's variations on pressure transient testing. And one of the types of pressure transient testing that you can do is an interference test, where you're looking perhaps for interference between an injector in a water flood and a producing well. Perhaps you have a 5-spot pattern. And a certain type of interference test is called a pulse test, where you turn injectors on and off, and you see if there's a pressure response at the producing well. So if you're concerned about a direct communication and watering out because there's a direct channel from a water injection well in a water flood to a producing well, you can get a little more elaborate than the standard static bottom hole pressure test, fluid level test, and use the pressure transient option to see if you have some interference between them.
Thanks. I have another question from Dan. And actually, this question already had 2 comments on the chat, and thanks to Ling and Chanel. The question is, we have been shooting fluid levels in all our shutting wells. Most our horizontal are on gas lift. I'm getting many fluid levels past the end of tubing, even seen top of perforation a couple of times. Is this normal? And I would say yes. This is actually even more normal, like an everyday rule for gas well. But as Lynn said in one of his comments on the chat, all wells they have high gas pressure zones, then it is common to see the liquid level pushed out of the tubing and into the perforations. And also, Chanel is complimenting that answer and says, I recall a build-up exercise on a low PHP well. The gas production GOR was unknown, and every day the static fluid level kept dropping, perforations and casing head pressure increased. If you want to add something to that.
Yeah, I'll add a little bit onto that. My initial experience in the oil field, I spent the first 10 years of my career out in the Permian Basin, and I did a fair amount of pressure transient testing at that time, doing buildup testing on conventional vertical wells, the older wells that have been around for a long period of time. And what I found on a lot of the buildup tests that I did was that the fluid level was depressed. You know, as the surface pressure increased, it would push a lot of the fluid back into the formation. And that was actually a good thing, because the biggest unknown or perhaps source of inaccuracy in the calculations is the gradient of the fluid column. And if those liquids are being pushed back into the formation, we do a pretty good job of estimating that gas column gradient, that it does contribute to having a more accurate answer.
Thanks. Yes, go ahead, Dr. Podio, please.
Dieter, one more comment. The question was related to horizontal wells, and one thing to remember is that a lot of these horizontal wells are producing at very, very high gas liquid ratios. And so you have a very high gaseous column above the pump intake. And when you shut in, that liquid will fall back, and it may have been only 10-15% liquid and the rest is gas. So you don't have enough liquid to fill the annulus and then fill also the bottom of the well. It's something else to consider, that even though you have a high gaseous liquid column, there isn't that much liquid in that column.
I would say that most of the fluid levels I've seen on shale wells are essentially a mist in the annulus. You know, it's probably less than 20% liquid in the annulus because of the high gas flow rate, like you mentioned, Tony.
Thank you. We have an interesting question from Ken. He's asking, in commingled wells, how is the static borehole pressure calculated for both zones?
We can't really calculate it independently. What you can do is, in the TAM software or in the TWM software, change the formation depth to the depth of those two different zones and calculate the pressures at those zones. What we don't really know is if one zone is a higher pressure zone than the other zone, and if you have cross flow from one zone into the other. The best we can do is calculate the pressure and a liquid column at the height of that formation, that zone. Tony, you got any comments?
No, I think that's all. It's always an uncertainty. The more zones you have perforated, the less information you have.
All right. Okay, we have one more question. Well, a couple of more questions. One is from Yula Tang. He's asking, how do you determine oil column and water column in static borehole pressure? I think we covered a little bit about that, but if you can refresh, how do we determine the oil and water column in static borehole pressure shots?
Hello, Eula. Yeah, I think we touched on that, where we get the producing shot as our baseline, and then we just use our water-oil ratio to determine the height of the oil and water column in there. And I think as you work through the example that's coming up, Gustavo, it'll show that a little bit.
Yeah, I will cover that too. And Ken's asking, how is the static borehole pressure calculated in an S-curve well, highly deviated?
And I'm glad that was brought up, because all of these calculations are based on vertical depth. And in the wellbore information, in the well file in TAM, especially when we look in a detailed view, there's a place to enter the deviation survey of the well. And that can, everything we do in the well on a liquid level, in terms of the well bore itself, the pump depth, everything is based on a measured depth, formation depth. That's all measured on measured depths. But to do these static bottom hole pressure, or even a producing bottom hole pressure on a deviated well, an S-shaped well, or a horizontal, we have to convert all those measured depths to a vertical height. And it uses the deviation survey that you enter into the well file to do that.
Good point. Well, a more operational question from Jason Brett. He says, is there too much pressure when charging a fluid level gun with CO2?
There's not. I'd say yes, there can be too much pressure. Perhaps especially in a static situation. Typically, where I see too much pressure on the gun is if the liquid level approaches the surface.
Sure.
And the shot is so big that it might be hard to see the fluid level reflection because you're still in that initial part of the shot. And I've had people call me where they took fluid levels on took shots on high liquid levels that were perhaps 75 feet, 90, 100 feet from surface, and they couldn't see it because the shot was so big. So I would tell them to put as little pressure on the gun as it takes to fire the gun, perhaps 75 PSI. And a lot of times they were at the well when they called up, and they said, Dieter, wait on the phone. If you don't mind, I'm all hooked up. I'm going to try that. And they'd come back and they'd say, wow, that worked. I see the liquid level now. It was 3 joints down from surface. So if you have a high fluid level, especially, you can take too big of a shot. In general, it doesn't hurt you, but you don't if on a deeper liquid level. But again, on a static shot, since the well's quiet, you just don't need as big of a shot. And if I'm going to a well that I haven't been to before, I'm always going to start out with a little bigger shot, perhaps, just to make sure I get it. But once you've been on that well and know what you do, you'll know the minimum amount it takes to get it and just use that.
Well, one more question before we go to the sample, and that's from Tariq. He's asking, how accurate will the fluid level data be after taking shot with a liner in hole? Took data, I guess he took data with TWM and Model M for comparison while the well was off. Can you shed any light on when these wells are shut in and also monitoring intervals?
Okay. Thank you, Tariq. I don't know if your liquid level was above or below the liner that you had in the well. If your liquid level's below the liner actually becomes a useful tool for ensuring that your liquid level's accurate. For one, we can use the marker method, and let's see.
It was below. It was below the fluid level.
Oh, very good. So you can use the liner top as a marker or as a reference. And in the software, in both TWM and TAM, you can put a marker at the liner top. And let's just say the liner top's 5,000 feet, and it knows the number of seconds it took to get to the liner top. Then it comes up with a very good number to use for the acoustic velocity and get that. Say you're using another method like acoustic velocity or collars, an option you have in both TWM and TAM is a depth reference line. And you can move that line to any point in the well bore, and you could move it to the liner top and just see if it's accurate there, see how close that is to where it actually is. But I would use the liner top as a marker, use the marker method for analysis, and it should give you an even better liquid level than not having a liner in the well, more accurate. And Tariq, if you have any questions or have any data, as far as anybody goes, feel free to email your data to us. You can send it to info@echometer.com or to Dieter@echometer.com, and we'll be glad to look at your data and answer it more specifically.
Well, if we have time for one more question, just came in from Anil Yoshi. It says, in one of the graphs, you have shown a static borehole pressure at 1,000 psi and a borehole pressure, producing borehole pressure at 500 psi. If the yield of this well is more than pumping capacity, how can you determine producing borehole pressure?
Okay, we can determine, Anil, we can determine the producing bottom hole pressure from the producing shot. We can determine what that is at that point of time. And I think I'll defer to Tony, because Tony, after Gustavo works through this example, is going to talk about inflow performance relationships, and he could tell you what the predict what the pumping rate would be at or what the bottom hole pressure would be at different pumping rates, and what it would perhaps be at the capacity of your lift equipment if you're not at capacity right now. Tony, you have any thoughts on that? Or I think that kind of fits in with your IPR calculations in a way.
Yeah, I think you're right. We'll talk about that in just a minute.
Okay.
Well, then I'm going to go ahead and talk about that static borehole pressure example. I hope you can see it now. And well, yes, we're going to present you one well that the well is going to be shown to you is a well that you should all have in your CAM or TWN software. It's a part of the examples. It's a PFL static borehole pressure well. So for the ones who are not familiar with the TAM software, we just got to pick a well, and we might either scroll to where our well is at. Then we have a producing fluid level, or if you just know part of the name of the well, you just may type it, and we can start with static borehole pressure, and you can quickly pick your well from there. And the first thing I want to highlight here, this is a rod pump well. It's not a gas lift or a gas well, so we're expecting to see a build up in the fluid level when we shut in the well, as we don't have such a high gas production or high gas pressure on the well. And this is a rod pump well with a lofting unit 640 and 168 stroke length with an 1 3/4 pump. And one of the things we want to show you is the number of shots that we have for having kind of a complete reference on the well potential on the calculation of the static borehole pressure. And if we click on the liquid level history, we have a range here from the oldest fluid level to the newest. They are arranged. So we're going to be reviewing the very first fluid level on the example, which was January the 4th. This is a null fluid level shot. And on this fluid level, this will be, as Dieter mentioned, our baseline, where we want to check. That was exactly when the well was, just before the well was stopped or shut in. And for the ones who are not familiarized with the liquid level analysis, we can see a clear fluid level shot with kind of a good fluid level kick, and we have a method calculation of color counts. We can see a color count line very close to the liquid level, and if we check more in detail, if you want to, we can see that the software was able to count over 90% of the color. So we should have a very good calculation of the liquid level distance from surface. We also have a build-up test with a small incremental pressure or pressure build-up during the test. And on this well, we might be looking at, and on the report, I'm going to be more details in the next shots, but one of the highlights here is the software determined the fluid level is 6,808 feet from surface. That results in almost 900 feet of fluid level, fluid above the pump. And from that liquid gases column, only 782 feet are liquid. So the software will consider this distance of oil above the pump for the future pressure calculation. So again, we're reviewing the producing condition of the well just before shut in. So once we have this will be our baseline, and we can perform extra analysis like a dyno car for a rod pump well, and to understand how the pump is working and having a more complete system performance analysis. So that was the first shot, and 4 days later, the well reached the static condition, and probably the well was monitored. I'm gonna take some of the reference lines off, and we have a fluid level now that's been raised to 3,600 feet, and this represents a big incremental on the fluid level depth. So another thing that we need to consider is we check on the well information, we have some production data input in here. Comparing that production data with the well test, so we have on December, just about a month ago, the well was shut in, we have a production input, but also we have a production input on February the 6th, which was a day before that the fluid level, the second production fluid level was measured. We're gonna go back here in a minute. So having the second fluid level shot, waiting until 4 days, respecting the well was in a static condition. So let's go ahead and check the report. And we can see on the report on the left that the producing fluid level report looks different than the static fluid level reports. And one of the things that you might want to do at the beginning of the analysis on a static shot is you need to change the well status from producing into static if you don't have it there. This is very important for the software to understand how was the producing condition, and that will be considered the first fluid level shot that we had. So on that static shot, before going into the report details, let's check the static borehole pressure worksheet. And we have two options that Dieter mentioned. And we could either select one of the previous fluid level shots or manually enter the shot. Things that we need to consider is on this screen, you will have all available fluid level shots in the well. So be careful, do not select the fluid level that was earlier or that was measured after the static fluid level. As we can see here, the date of the fluid level was January the 8th, and we have some fluid level from February. So we're going to take January the 4th of the previous fluid level under production condition to calculate or estimate the static borehole pressure. If you don't have, and that's a very common question, is if you don't have a previous fluid level, like many wells are just shut in because of any existing condition, and then they need to go and manually enter the information, it's important that you have the most accurate information possible. So the software will actually use the information measured and calculated from the producing fluid level shot, and we're going to discuss about that right now, to calculate or estimate the static borehole pressure. So on the left of the static borehole pressure report, we have the producing shot and give us the date and time so we can double check and confirm what we're using. And then we have the time of it and what was the buildup at that point, the casing pressure, and some information from the producing condition. On the right, we have the static shot, which was just these results. So the fluid level is at 3,612. And a picture with the fluid distribution estimated for the software based on the new fluid level shot, the previous producing condition, and the well test information. And something to highlight is the software, despite having more than one well test information, it will take the closest previous well test information to estimate the liquid columns in the anodes. So by having a well test of 246 barrels a day, and we can come back and check in production just to confirm that this is the information the software was using at that point, the flue level was measured and is using the producing information from the previous flue level. So we have that, and when we will check the producing flue level after the well was restarted, then we will be able to use the February well test to estimate the well potential. So on this, we have in the center, we have the pressure profile, starting with the casing pressure, the gas column or gas gradient, and the oil column gradient, and the water column gradient. The software is calculating 1,868 psi as a starting borehole pressure, and that is the result of the three columns, the gas column, and the oil column, and the water column. And these calculations are not difficult, of course. This is a vertical well, and there was a question on where the survey was important to input, and in the software, for the ones who are not familiar with, there was a question from Ken about an S-type well. And in this point of the software is where you can input the measure and true vertical depth in the software, so we will calculate the equivalent true vertical column or distance or height of each of these gas, oil, and water column in the well. Something that we can review is the software will use this information, but just we need to be sure that we update the software study borehole pressure information when we are analyzing the well after it's restarted. So let's jump to the third flue level, and this you can see was a month later. The well was already running, and this is the producing condition. We can observe the flue level is a little higher, and checking on the report, we have a new well test being considered. So this is not 246 barrels a day, but 224. And this is a different, again, well test that performed just the day before the flue level was performed. So the people analyzing this well was really focused on having as much accurate information as possible to have a representative well potential calculation. And Dr. Podio will talk about that in a minute. Checking the report, we can still see what the software is doing in terms of counting colors and distance to liquid level, and gas flow in the annulus, and liquid level calculation and liquid percentage in the annulus. So 1868.2 was a study borehole pressure calculated a month ago, but something that you need to do is you need to tell the software and update the information on the wellbore schematic and the producing interval. And this is the producing interval calculated at 7740. That was the study borehole pressure. So the software will be able to use that study borehole pressure recently measured to estimate the well potential. There was a question about or a comment about the casing liner, and yes, you could use any downhole marker in the well or any kick. And actually, the very first shot, if we look at the end of the shot, this is the flue level kick, and based on the wellbore diagram overlaid here, we have a tubing anchor above the flue level depth, and we could use this tubing anchor kick as a downhole marker if we don't have a good color count. And we're just analyzing the flue level based on the color count, which was very good and resulting in 1084 feet per second as an acoustic velocity. But if we check on the downhole marker methods and we select the kick from the tubing anchor, the resulting acoustic velocity is actually really close. It's 1086. So we have actually in this well both methods available, and they will have pretty much the same result or the same acoustic velocity calculation. So it looks to be very representative. Any comment you want to add, or we can go ahead and get probably some other questions here?
Yeah, Gustavo, can you go back? Can you open your report for that shot? No.
For the first or the last
the
one?
one that you just had on there. Open the report.
Yes.
Okay, can you zoom in a little bit so we can see a little bigger? Okay, thank you. What I want to point out here is that in the report, you have information about, at the top, just leave it at the top. It says fluid above pump is the total amount of fluid above the pump intake, and then the next number is the equivalent gas-free above the pump. So this is in information about the conditions above the pump intake. The next rectangle there, where it says production, it has information about the IPR method, and it says Vogel, and that is what the program uses as a default, is the method, the IPR method that it uses by default. And the two numbers that are listed there, one says is the ratio of the producing bottom hole pressure to the static bottom hole pressure, 0.36, and then below there you have the producing efficiency, which is 81.66%. And so we're going to talk about how those numbers are computed by the program. Thank you.
And in a vertical well, actually, you can easily estimate what the software is doing by having the difference in the fluid levels, like in this well. If you want to confirm what the software is doing, and you might just take some information like the difference in the columns. We had a fluid level at 6804, and then we had a fluid level at 3612. But consider that the software will be using only 782 feet of gas-free column, which is 782 feet of oil. So that will be our initial oil column from the new 3,310 fluid that came from the producing into the static condition. We have a new oil column based on the water cut and all the well test information of 484 feet. So if we have a total initial and new oil column of 1267, and that's pretty much what the software is calculating. If we open the report, that would be 1267, and the water will be the same. So we have only 40 feet between perforations and pump, which is the assumption that we have when the well is producing in a stable condition, that from the pump intake to the perforations, we have a water column, plus the water that came in the afterflow after the well was shut in. So if we add those, that would be 2840. So the software is actually considering the initial fluid level shot and the amount of oil above the pump, together with the fluid level and the static condition and the well test information to estimate the borehole pressure. And I'm recapping that because we had a question on how do we calculate this from, I think, July 10. Well, if you don't have any other comment, let's go with some other questions that have been coming in here before we jump into the well potential calculation and the inflow performance relationship from Dr. Podio. Let's see, we have a few questions, and Anil is saying, in one of the graphs you have shown, I think already did that, and Juan Carnaque is asking how to correctly calculate the liquid level column in a well with very high submergency. Sometimes the software calculates a high liquid column, and at other times it calculates a high gas flow. The liquid level signal is located at almost the same depth in similar production conditions. And probably Dr. Podio may chime in on gas buildup, that very likely affecting the calculations.
I think I would have to look at the data to be able to answer this question intelligently.
And
I'm not
usually,
sure I understand it.
Yeah, and I usually the difference in the liquid level, not the liquid level, but the amount of liquid in the annulus is related to a difference in the build-up tests, how they were conducted, how long they run the test, and so on. But definitely, Juan, we would like to see your data and try to have a fair answer for that. Another question from Sam Barkey says, how do you find out the production interval? I'm not sure that I get the question, but the production interval is an input that you need to get before you shoot the fluid level. And where do you expect to calculate the pressures on?
So they would have to come up with that from their wellbore schematic or perforating records or.
Yeah, but definitely it's an input that you need to find out as part of the well information that you need to run the fluid level tests. Okay, Jonathan's asking if we can send an Excel that I show. Well, just a quick Excel. It shows the static shot, no need for multi-phase S-curve calibration, right? Just assuming pure water and oil and no gas in liquid. Well, the calculation, Jula, is related to a static well. So yes, there is no gas in the liquid right now. You have a gas column on top of that, but then you have oil and gas based on, as we said before, the previous fluid level shot on the producing condition and the well test information. Let's continue. Let's show the presentation from that point. So Dr. Podio can start showing his presentation.
So this is what we're trying to establish is what we call the well performance. And in order to do that, we said that we need to have a good estimate of the static bottom hole pressure. So now that we have that, we've seen that we can get that from the shut-in condition of the well. What are we going to do with that information? And there are at least three things that we can determine. One is the well performance establishes the relationship between the flow rate that we are producing, the flow rate that we're pumping, and the pressure. And so we can establish what is the pressure drawdown that corresponds to a given production rate. And then once we have that at a certain rate, what we would like to do is to establish at what rate am I going to pump off the well. And by pump off, I mean, when will the fluid level reach, at what rate will the fluid level reach the pump intake, which is the limit that I can produce given the current installation. If I want to produce the complete capability, the potential of the well, I would have to have the pump intake at the formation depth. And in many, many wells, especially the horizontal wells, we know that we have the pump intake is way above the producing formation. And so this is what we can establish is what is going to be the rate that will cause the fluid level to drop to the pump intake. And so these quantities are determined by establishing a relation between the pumping rate and the producing bottom pressure. And this is known as the IPR or inflow performance of the well. And the next slide shows that if I want to establish that relationship accurately, what I have to do is I have to perform what is known as a multi-rate test. The multi-rate test involves running the pump at different producing rate, either starting with the well shut in, as indicated in the figures here on the right. You have a pressure versus time. Initially, the well is shut in. The pressure is at the static pressure. You turn on the pump at a certain rate, the pressure drops to T1. You increase the pump rate, the pressure drops to T2. And you increase the pumping rate, and the pressure drops to 3. And so how do you get this pressure? Well, you can either use a downhole pressure sensor, and this is fairly common on ESP wells, but in rod pumping wells, the only practical way of doing this is by taking fluid level measurements at each one of the rates. Once you have this information, you can make a graph as is shown is on the left, where the horizontal axis is the flow rate. And we have the 3 flow rates that we have established, Q1, Q2, and Q3. And the vertical axis is the pressure that we have at the well bore for that particular rate. So the curve in black then represents the inflow performance of the particular well. And when the rate reaches past Q3, all the pressure has been expended, and we have essentially zero pressure at the wellbore. That is the point where we would call, or we would define as being the potential of the well. Now, if we have a variable speed drive, we have the capability of doing this fairly easily, but it also requires a certain amount of time. And so very seldom you have these IPRs determined by means of a variable rate test. In the next slide, we say that there are other methods, and one method that was developed by Vogel. It is a generalized inflow performance relationship, and it allows to estimate the inflow performance relation using only one well test, only one data point, and using the static bottom hole pressure. It describes the well performance when both free gas and liquid flow simultaneously from the reservoir. So it is the most general case, and so it is used quite often, and it is generally accepted. The main advantage of the Vogel relation is that it allows determining the performance using only one stabilized flow rate. It doesn't require a multi-rate test. In the next slide, what this slide shows is the relationship or the comparison. The curve in black is the inflow performance if we had run a multi-rate test. And the blue curve is the Vogel inflow performance that is generated using only one well test. So we have a well test information. We measure the producing bottom hole pressure. We determine the reservoir pressure, which is the static bottom hole pressure. So having those two pieces of information, we can then calculate the potential, the Qmax of the well. So this is one of the reasons why the Vogel relation is used extensively, because it does do a reasonable approximation of the actual inflow performance, and it requires only the well test. One problem that I want to mention here is that very often the production from different wells are commingled, and so it is not very simple to obtain an accurate well test. And by well test, we're talking about the liquid rate that is produced, and that includes oil and water. So we have one problem is very often the oil rate is measured accurately, the water rate is not measured very accurately. And in many cases, the wells are commingled, the production from the wells are commingled, so it is not easy to estimate what the production rate is. One advantage of having a rod pump well is that if you have a good dynamometer measurement and you do a detailed analysis of the pump dynamometer, from the pump dynamometer you can establish an accurate flow rate that the well is producing. And I think there will be a presentation on that subject coming up in the future. So you may want to make sure that you don't miss that one. The next slide, what I'm presenting here is a different way of looking at this, more from a practical standpoint. Now that we have a static fluid level measurement, and we know the static fluid level measurement corrected for any gas-free, and we have a producing gas fluid above pump corrected for the gas being produced. If we take the ratio of these two values, is an estimate of the pump rate that will draw the fluid down to the pump intake and achieve pump off. And so in the next slide, we have the example that Gustavo looked at a while ago. And you notice that we did a static fluid level measurement. It says that we have 4,092 feet of gas-free liquid above the pump intake. So this is above the pump intake. The producing fluid level was taken a month later, and it shows 1,636 feet of gas-free fluid above the pump. So the question is, I have pumped this well down to this fluid level. The liquid level is at 5,980. I still have 1,636 feet of gas-free fluid above the pump. Am I producing the well efficiently, or could I increase the pumping speed? And how much could I be producing until the fluid level reaches the pump intake? So I can use these two quantities in the Vogel curve in the next slide. And so I am using the Vogel curve, but instead of plotting the ratio of the pressures, I'm plotting the ratio of the gas-free fluid above the pump, the 1636, divided by the static fluid above the pump, 4,092. And I plot that on the vertical axis. That gives about 0.4. And it tells me that I am producing at 80% of the pump off rate. My current well test is 224 barrels per day. So I divide that by the percentage, and it says I could increase my pump rate up to 280 barrels per day, and that will cause my fluid level to drop to the pump intake. If I wanted to produce more than that, I would have to lower the pump intake. So that would require a workover of my well. But with the current completion, this is the maximum rate that I could produce. And so the next slide summarizes what I just said, that if you do this pumper IPR, it determines the producing gas-free fluid above the pump, compare it to the static fluid above the pump, and then when this ratio is less than 10%, then you are already producing about 95% of the pump off rate. So it's a quick and easy way of determining where you are in relation to what you could produce with the pump intake set at the current depth. And so I'm going to turn it over back to Dieter so that he can conclude the presentation.
Well, I hope that you found today useful, and you found that the static bottom hole pressure is a real important part of determining the well performance. It's a piece of information we need to solve the puzzle. And we can get fairly good estimates of the static bottom hole pressure off of the fluid level measurements. And while we have the chance, we should get this on all the wells that are shut in for any operational reason. So the more static bottom hole pressure information we have, the better off we are. We'll see variations between the field, depletion changes throughout the field, and so on. And then we having that and the producing bottom hole pressure, we can determine the well's performance. And the longer the well's shut in, the more representative we'll get of the reservoir pressure. And Eula, I saw your comment there saying that it can take months on some of the unconventional wells in the Permian Basin. And yeah, those are tight shales, so a really tight well will take a long time to come up with that. Some of the more conventional wells, you might have it in a shorter period of time. I've seen it in some wells in a matter of hours, days, weeks, or even months. So, but the way is just shoot fluid levels and see when they stop changing. Then you're at the static condition. And again, in future parts of the series, we're going to talk about other ways to do this, coming up with a pressure transient test to give you a better estimate of reservoir pressure or P star at the off of the buildup, and that might be useful on some of the tighter shale wells. We hope you found this beneficial. Hope you've met more of our team through today's session, and we'll continue these. Let me turn over to Carrie Ann. She has some comments I think she's doing next week on gas lift wells, and from there we'll probably come back and do another one of the series on static bottom hole pressure wells. But thank you all for attending. We appreciate your attendance and your interest. Thank you.
And thank you guys for putting together a great session. I like all of that interaction with everybody. And we'd like to thank all of you guys for joining us today, for your great questions and feedback. We hope you enjoyed it and learned something new. In the event you have any follow-up questions, or if you have data that you want us to take a look at, we welcome calls and emails. You can even just respond to the invitation email if that would be a little bit easier for you, and we'll get your questions answered. Next week's session topic, as Dieter mentioned, is acoustic techniques to monitor and troubleshoot gas lift wells. So if you're on the registration list for the weekly sessions, you'll automatically receive a link to next week's session. Otherwise, please go on out to that Ask Echometer webpage, and you can register through there. So we appreciate your time today. We're so glad you joined us, and we look forward to seeing you all again next Wednesday. All right. Well, thank you, everyone. Y'all have a great week.